Okay, so let's review this again. We have a structure here, and it wants to find the horizontal and vertical reactions at A and C down here. We know that at a pin, A, there's 2. And C is also a pin, that's 2. So I have 4 unknowns. If I try to draw one free body of the whole system, I generate 3 equations. Well, 3 equations will not solve for 4 unknowns. So this problem has a feature that, if not careful, you'll overlook. It's that you have a pin at B. So that will give us the ability to separate the structure there. That would create 2 unknowns at A, 2 unknowns at B, 2 more at C. That's 6, but then 2 free bodies. Each free body with 3 equations. That'd be 6 equations and 6 unknowns. So, as we talked about earlier, you can solve it that way, and you would be successful. But there's one unique feature that I want to bring up is, again, this section to the right, the BC section. Why is it unique? There are no applied loads on it. It's pinned at each end, so that's going to be a 2-force member. So just to indicate that, so that you won't forget, we're going to say that this is a 2-force member. Which means we know the line of action is going to fall between the pin along this line. So I know that that reaction there will be a force along that line of action going in that direction. I'll just call it B. With that, I'm going to come down here and now just draw a free body diagram of section AB. And let's see what we can do with that. So here's the AB. We know A is a pin, so I'm going to assume unknowns AY and AX. We've already discussed this situation, so I'm going to assume that I have this reaction up here. I'll call it B. What is this orientation? Well, it looks like it's going to go for it's going to drop a distance of 5 meters and then go over a distance of 4. So what is that, a 4-5 triangle? Kind of an odd triangle. But that's what it's going to do. So if I look at the actual slope of this, it would drop 5 and go 4. We can figure out that angle later when we need dimensions. On top of that, I have a distributed load. Now, how do we handle distributed loads? We like to use a concentrated equivalent. So this is a rectangular load. So we know the area of a rectangle is the base times the height. The base in this case is 5 meters. The height is 350. So what is that, 1750? So that'll happen here, and I'll indicate that's an equivalent load. And that's going to be 1750 newtons. And it's going to occur where? Well, the centroid of the rectangle is right in the middle, so that'd be half the distance. Yeah, so these dimensions are 2.5 and 2.5. That's meters. I left off the unit, sorry. So there's my free body diagram. Sorry, I think we're up to you. What do you want to do first? There's actually several ways to start, if you'd like.
Take the moment at A.
That's a great spot. Take the moment at A. Why is A a good choice? Well, there's 2 unknowns at A that will create no moment. So let's do that. So I'm going to use my right-hand rule for sign convention, and I'm going to sum moments about A and make sure it's an equilibrium. Mr. Brown, what's the moment about A for this 1750? Is it positive or negative?
That is negative.
Right. What's the moment arm?
2.5.
Correct. Everybody see that? Mr. Street, what's the moment of the B about A? I'll give you a hint. I suggest that we break it down into an X and a Y component. If I do that, then which component creates moment about A? The X component. What would be the X component about that? I do it a funny way. I go ahead and calculate the sine of angle in my head as the opposite over the hypotenuse. What's the hypotenuse of a 4 or 5 triangle? It would be 25 squared plus 4 squared, which is what? Oh, let's leave it in a rational form. What would it be? 25 plus 16 is, what is that? 41. So it would be, you're going to love this, it would be 4 over the square root of 41 times b. And what would this component be? 5 over the square root of 41b. Now, a lot of times what will happen in your book is this will be like 3/4. Well, that means the hypotenuse is 5. So these angles are going to be 4/5 and 3/5. So keep an eye out for that. The author loves to give you directions that are basically 3, 4, 5 triangles. Now he'll disguise them. It may be 12, 15, or something like that. But if you look at for common denominators, you'll get a lot of 3, 4, 5s. In this case, we were close. But for me up here, that's one less calculation I have to deal with here. So this is nice for me. Now back to you, Mr. Street. With that as the component, what's the moment?
4 over 41 b times 5.
Is that positive or negative? Negative. What was it, 5?
5.
So now you can see the thing you need is B, and it looks like in this calculation that B is going to be negative. I don't know what that is off the top of my head. I'm guessing it's 875. I don't have any idea. Somebody help me. 800. I'm revising my answer. It's a pure guess. Anybody get anything? Come on. Get out your slide rule and try it with that. Nobody?
1400.
Exactly?
0.68.
1400? Anybody getting 1400? Oh, some heads are shaking now. 1400 point. I'll just do 0.6. Is it 0.6 is good enough?
0.7.
0.7?
0.7.
And that should be in newtons. That kind of makes sense, don't you think? If I'm rotating about A, since this force is causing the structure to want to rotate counterclockwise, this one better push back. That makes sense. Okay, what's left? Mr. McBride, what do we do next?
Sum the forces of X.
Why not? We're going to sum the forces in the x direction. Why is that a good choice? Because there's only one unknown, right? All right, so we're back to the special table. Ducius, what's the sum of the forces in the x direction?
We got 1750 positive.
Okay.
And then we got positive b 4 over square root of 41.
Did you say 4?
Positive b 4 over square root of 41.
Okay. Yeah. And what else? What are we looking for?
Oh, yeah, AX.
Okay, so when we plug B into here, what value do we plug in? negative 1400. So what is AX? Negative 875. Anybody else get that? Yep. And that's newtons. Mr. Montgomery, what do we have to do next? Some forces in the Y. I like that. Basically, we don't have any choice, right? Mr. Birmingham, do that for us.
AY minus 4 over the square root of 41b.
Not 4, we're going in the Y direction, so we want this guy, which is 5. And again, we're going to plug in the negative value for B, so it looks like AY is going to be negative, right? And what's that value? What'd you get?
Negative 1093.8.
1093.8? Yep. 1093.8. Messy problem. Wow. I was wrong all over the place. But does it matter? No. I assume the wrong direction every time. I don't feel bad about it. Because it is what it is, right? Are we done? No. What do we have to do next? I got to find the reactions at C. So if I assume this force was acting down in this direction, what's it on the other side? It's equal and opposite, correct? So let's do this. I know it's going to be a little strange, but I didn't give myself enough. Well, maybe I can squeeze it down here. So let's look at right here at C. Can I do that? Can I draw a free body diagram of C? Sure I can. So if this force is pulling up here, I think I called it B, right? And then I'm going to assume my reactions are CY and CX. How can I find those? Oh, I'm sorry, I ran off of it. Give me a second, I can make a small adjustment. There we go. So it seems all I need to do is what? Get the X component and the Y component, and away I go. What's the Y component? Don't forget it's the same as it was before, right? This is a, I'm really sorry, I'm really small. There's a 5, 4. So the Y component is going to be B times 5 over the square root of 41, right? And the X component is going to be 4 square root of 41B. I do that right? So I guess we're back to Mr. Reddick. How do we solve for CX and CY? Or pick one.
Doesn't matter.
Pick one.
CY.
You want to do Y? So that means in the Y direction, I'll sum the forces. Mr. Monterey, what's the sum of the forces in the Y direction? Oh, with using my free body diagram. Can you see it?
B times 5 over square root of 41. Plus CY.
That looks good to me. So what's CY equal to? The negative of that, right? And what's B? Negative 1400. So what is C? I don't know what that is. What's 1400 times 5 divided by square root of 41?
1093.8.
Is it really?
Yeah.
Wow. And it is positive, right? So it is up. What about, let's see, who's next? Mr. Mokhtari, what do we do?
For CX, it's just going to be the opposite of AX, so it would be negative 1,750 minus 4 over square root of 41 times B.
Correct. So I'm going to go ahead and let me just write the equation. I think you're saying the right thing. So it's going to be CX minus 4 square root of 41B. You plug that in there, what's CX?
It's going to be positive
875. Also, positive or negative? Negative. Right? Because you plug a negative in for B, this becomes positive. You have to throw it to the other side of the equation, it becomes negative. So both the X components are to the left, reacting with the applied force, which is to the right. Oh yeah, that was a good one, huh? That took 16 minutes and 33 seconds. But I was talking to you and telling you bad jokes and picking on the small table and all those other things. Any other questions about this one?